So today I want to introduce to you section 10.3, which is about polar coordinates. So in this section I will introduce a new kind of coordinate system. It's called polar coordinate system, and it might help us for certain situations. Rather than using rectangular, we'll use polar. You will see what I'm talking about. So what exactly is or are polar coordinates? A polar coordinate system in a plane, so working in 2 dimensions, consists of a fixed point O. That fixed point O called the pole, which is exactly the origin in rectangular coordinates, and a horizontal ray emanating from the pole directed to the right of O. So basically the horizontal ray, which is called polar axis, is what we know as the positive side of the x-axis in rectangle, okay? Positive x-axis. So we have what we call the pole, and we have the polar axis. Okay, so instead of using x and y axes, that's what we have in polar. The coordinates are in polar, the coordinates are r and theta. R is the directed distance, so it could be positive or negative, from O to P, or to any point P. And theta is the directing angle, again it could be positive or negative, from polar axis to the terminal side P, to the terminal side of P. So, 2 things. To measure R, you always start at the pole. To measure theta, you always start at the polar axis, which is the positive x-axis. If you're going clockwise, theta is positive. If you're going counterclockwise, theta is negative, okay? As always. So this is the polar axis. So if I go this way, this is theta, and theta is positive, that's point P, this is R. I go this way, again, that's theta, which is negative, and point P. Okay, this is the terminal side of theta. Alright, so let's look at some special cases. Let's look at special cases. The first special case, if P at the pole, if the point P at pole, which is at O, if P is right here, this is the polar axis, so P is O, then R is 0, obviously, right? Because P is the distance from O to P. I mean, R is the distance from O to P, so it's 0. And there is no clear polar angle theta in this case, okay? Because theta is the angle between OP and the polar axis, so no clear theta. So 0 theta, it could be the coordinates of the pole, where theta could be anything. Any choice of theta, okay? 0, no. I mean, theta has to be from the polar axis to the terminal axis, but there is no terminal axis. The polar coordinate of a point are not unique. So each polar coordinate, each polar coordinate has an infinite number of representations, okay? Unlike rectangular, one point has one x and one y. This has an infinite number of representation. For example, the point 1 pi over 3 is the same thing as 1 negative 5 pi over 3 is the same thing as 1 7 pi over 3 is the same thing as negative 1 negative 2 pi over 3. All these represent the same point. So if you look at this is the polar axis, the pole. So this is 90 degrees. Pi over 3 is somewhere there, 60 degrees. So a point, this is, say this is 1 unit. So this would be 1 pi over 3. Point P is the same thing as 1 negative 5 pi over 3. So if you start here and go that way, that's going to give you 1 negative 5 pi over 3. If you go 7 pi over 3 is, if you notice, because if you do pi over 3 plus 2 pi, it's pi over 3 plus 6 pi over 3, which gives you that. So every time you add 2 pi, it gets you back to the same point. So that's why 7 pi over 3 is the same as 1 pi over 3, because pi over 3 plus 2 pi will take you back to the same angle. Now this is what we gotta be careful about. Negative 1. Okay, so 7 pi over 3 is the same because you're adding, 7 pi over 3 is pi over 3 plus 2 pi. So if you add 2 pi, it takes you back to the same angle. Okay, now this is what you got to be careful about, the negative 2 pi over 3. The negative 2 pi over 3. The negative 1, negative 2 pi over 3. So if you negative 2 pi over 3, it's pi over 3 short of, so basically you're coming this way, and if you measure backward to get to this point, you see we always start at the pole and go along the terminal side of, in this case, negative 5 pi over 3. This is negative 5 pi over 3. If you go forward, it's positive r. If you go backward, it's negative r. That's why this is negative 2 pi over 3. That's why you have a negative 1 here. You're not coming this way to get the point P, you have to go backwards. So you measure backwards, r is negative, okay? And so on. There's infinitely many representations for a single point in polar coordinates. So basically, if P R theta is a point, then it's the same thing as r plus r theta plus 2n pi. If you add multiples of n is an integer. If you add multiples of 2 pi, you're going to get the same point. Also, negative r theta, and for any theta, r theta plus pi are polar coordinates of the same point. So let me explain that. If I want to do theta, so if I assume this is theta, and if I go this way, it's positive r. If I go that way, it's negative, right? I go forward on, this is the terminal side always. If I measure along the terminal side of theta, it's positive r. If I go this way, so this is r, and so this would be negative r theta. We're saying that's the same thing as r theta plus pi. So basically, if you go theta and then pi more, that's theta plus pi, all this. And then this is the terminal side of theta plus pi. So you're going to go forward because you're measuring along the terminal side, so this is going to be r. And that's the same thing. These two are the same. Okay. All right. So here's more examples. Find alternative polar coordinate representation, polar coordinate representation of 0.63 pi over 4 that satisfy part A, r is greater than 0, theta is less than 0. You could use graphing polar graphs. I mean, I researched the website and I got few nice ones. It's kind of blurry though. Let's see. We try to zoom in. Okay. I don't know if you can see. It's kind of small. So I just did 0, pi over 6, pi over 3, pi over 2, and so on. Yeah, 2 pi over 3. Let's see if we can zoom on this one. No. Okay. So if you want to draw, say, 6, 3 pi over 4, so you go like this, 3 pi over 4. This is 3 pi over 4. Well, I didn't do pi over 4, so pi over 6, 2 pi over 6. So this would be pi over 4. This is pi over 2 or 2 pi over 4. This would be 3 pi over 4 at this point. Okay. So you go with the angle. This is your polar axis right there. You go 3 pi over 4. Stay there. Then you measure 6 units there. 1, 2, 3. So 1, 2, 3, 4, 5, 6. So this would be 6, 3 pi over 4. Okay. I don't know if this is any easier, but okay. Maybe I should, because I don't like those circles here. It's not showing clear picture, but this is the best that I could find right now. All right, so how do we find a better representation? I mean, a representation where r is greater than 0 and theta is negative. So we want theta to be negative, but r still be positive 6. So to get theta negative, we have to go this way, but r has to be positive. So we cannot stop at this angle, because then r would be negative, because it will have to go backwards. So we start here and then go all the way there, and then that angle is going to be pi plus pi over 4, which is negative 5 pi over 4. So it'll be negative 5 pi over 4 and then 6. Okay. And then part B, if I want to do r positive, theta is greater than 2 pi. So all we have to do for theta to be more than 2 pi is take this and add 2 pi to it. So it would be 3 pi over 4 plus 8 pi over 4, which is 11 pi over 4. So that would give you the representation. I'll do one more. I have 2 more there, but I'll do one more. R is theta, R is negative, and theta is positive. So theta has to be positive, but R has to be negative. That means we have to measure backwards. So theta has to be positive. If I stop here, R will be positive. So I have to go all the way to here. And no, to there. So this would be all that, that's going to be 7 pi over 4, all that, and then r would be negative, so it would be negative 6, 7 pi over 4. Okay, so you can play around with this. So now, how do we convert from polar to rectangular and vice versa? So conversion between polar and rectangular. Basically, if you take the polar axis or polar axis, which is the positive x-axis, and that's a theta equal 9 pi over 2, which is the y-axis, and if you do theta r, that's point P, which also has x and y, you can the connection. So to convert from polar to rectangular, that's the easier one, because there's unique representation for rectangular. X equals r cosine theta, y equals r sine theta, because cosine theta is adjacent over hypotenuse, so that gives me x equal r cosine, and then sine theta is opposite over hypotenuse, that gives me y equals r sine theta. And if you do x squared plus y squared, you get r squared, because cosine squared plus sine squared is 1. Now if you want to do rectangular, that's when you have to be careful. To polar from, so you're given xy, you need to find r theta. So r squared, you use this formula, x squared plus y squared to get r, and then theta, you could do sine theta equals y over r. You could do tangent theta, x over r, or I'm sorry, cosine theta. But it's best to do tangent because it doesn't have r, because r could be negative, so it's y over x. Tangent is opposite over adjacent. So let's look at number 6, page 692. Number 6, page 692. It says the Cartesian coordinates of a point are given. Find the polar coordinates where r is greater than 0 and theta between 0 and 2 pi, and then polar coordinates where r is negative. So there's two cases. Okay, so we're given the xy, which is root 3 negative 1. Part A, find r theta where r is positive and theta is between 0 and 2 pi. Alright, so to find r, remember r squared is x squared plus y squared. So it's root 3 squared plus negative 1 squared. 3 plus 1 is 4, so r is plus or minus 2. But r has to be positive in this case, and theta is between 0 and 2 pi. So tangent theta is y over x, negative 1 over root 3. So theta is so theta is, if you want theta to be positive between 0 and 2 pi, it's 11 pi over 6. So basically, you will have the polar axis. You want r to be 2, and theta is 11 pi over 6. All this is 11 pi over 6, so that's your terminal side. 11 pi over 6, and r is 2, so that would be the point. Okay, which is the same thing as root 3 -1. If you superimpose the rectangular along the polar, that's x. So this should be √3, and this should be -1. You can see. Part B, we want r to be negative, and theta is between 0 and 2 pi, but r has to be negative. So basically, we're gonna go to, instead of going all the way here, we're gonna go up to there. We're gonna stop right there. So this would be theta equals up to here 5 pi over 6. That's the terminal side of 5 pi over 6. So we're not going forward, we're going backward. So that's why it's going to be -r. So -2 5 pi over 6. Okay. So now to the graphs of polar equations. By the way, there's a summary of the graphs of polar functions and your textbook on page 691. It sums up all the polar graphs. Okay, so the first one, we're gonna do vertical lines versus horizontal lines. In rectangular, it's x equals a, y equals b. In polar, you know, x is r cosine theta, so r cosine theta equals a, r sine theta equals b. So basically, x equals a, so this is a, this is x equals a, and it's r cosine theta equals a. So if this is theta and this is r, so cosine theta is x over r, so r times cosine theta, which is x, equals a, as you can see. And this is y, so r sine theta equals b. So you can see that if we do it this way, this is point P, this is y, this is y equals b, this is theta, this is r, this is 0b, so this is b. So you can see the transition from polar to rectangle, from rectangular to polar. Okay. So for example, r cosine theta equals 1. It's like having x equals 1 in polar. So this is polar. This is polar axis. So it'd be, this is 1 here. So it'd be, this is r cosine theta equals 1. And r sine theta equals 2. It's like y equal 2 in rectangular. 1, 2. This is r sine theta equals 2. Okay, then we're going to talk about lines through the origin. So theta equals theta 0, where theta 0 is a constant, is a line through the pole, okay, or the origin. R could be anything. Just like in rectangular, when we say y equal 2, that means x could be anything, right? In polar, if we say theta equals a constant, that means r could be anything. Why is that true? Because if you're looking at lines through the origin, the equation is y equals mx. But y over x, if you divide by x, equals m. So if you do y, but you know that this is the same thing as tangent theta. So theta equals tangent inverse of m, which is a constant, and that's your theta 0. So you can see how line through the origin translates into theta equals theta 0. So for example, theta equals 2 pi over 3. This is the pole. 2 pi, that's pi over 2, 2 pi over 3. So it should be any, that's theta equals 2 pi over 3, okay? R could be anything, could be positive, could be negative, any point here would satisfy theta equals 2 pi over 3. Then we want to talk about, so we did lines, now we're going to talk about circles and polar coordinates. So first, if we do R equals A, it's a circle, center at the pole, and radius A. Why? Because R squared equals x squared plus y squared. So R is square root of x squared plus y squared. If that equals A, then x squared plus y squared equals A squared. And that gives you a circle and rectangle. Okay. So say I want to do R equals 2. It's a circle, center at the pole, and radius 2. Okay, and radius 2. And actually we can check this with the grapher. If you go to mode, we're going to change mode into rectangular from into polar. Go to y equal, and you can see now it's R. So say R equals 2. There we go. Circle, center at the pole, and radius 2. And you can do zoom trick to get a better photo. Maybe not better. Zoom. Let's do zoom square maybe. Yeah. Zoom. I'm trying all these things. Zoom fit. No. Let's do zoom 6. Okay. So it gives you the circle center at 0 is 2. Now if it's R equal a constant, so theta could be anything. If it's R equals 2a cosine theta, then this would be circle centered on the x-axis. That means y equals 0 and passes through the pole. The radius A, which is half that, and center is A0. So basically for something like this, R equal to a cosine theta, center is at A0, radius is A, so this is A, this is A, this is A. It will be like this. Okay, so remember cosine is synonym of x because cosine is x, sine is y. So when it's 2a cosine, it's on the x-axis. If you have a negative, it will be on the negative x-axis. And here's an example. Say you want to do R equals 4 cosine theta. So if you look at the grapher, R equals 4 cosine of theta. There we go. Okay. Let me try -5 to 5 to see if I get a better view here. 6. No, that's okay. 0.13. Okay, that's fine. So just like it looks like. Okay. And you can see if I have r equal negative, I insert a negative there, it's going to be stretched along the negative x-axis. And if I delete the negative, I do sine instead of cosine, it's going to be on the positive. And if I do negative sine, it's going to be along the negative y-axis. So keep that in mind. All these are listed, so I don't want to have to write all of them down. They're in the notes, okay? They're right here. And there's some examples of the next page. I showed you a few of them. So now I'm going to cardioids. Cardioids, they are heart-shaped. They are heart-shaped polar graphs, and they are of the form r equals a plus a cosine theta, a minus a cosine theta, a plus a sine theta, a minus a sine theta. These are the four shapes of cardioids. When it's the plus and cosine, it's gonna be a heart shape. See, when theta is 0, you get 2a, so that's gonna be a, and that's 2a. When theta is pi over 2 over here, it's gonna be a, and that's gonna be 0, and that's gonna be a. So basically, it's gonna stretch along the positive x-axis when you have a plus a. If it's a minus a cosine, it's going to stretch along the negative x-axis. Why is that? Because when theta is 0, cosine 0 is 1, so r is 0. When theta is pi, you get 2a. So that's theta pi, you get 2a. That's why. So it's going to stretch this way. A, negative a. So for example, before we go to sine, if you do r equal 2 plus 2 cosine of theta, you can see it's stretched along the positive x-axis. You can see 4 units along x, and there is 2 units on the y-axis, okay? If you change that into minus, it's gonna flip around along the y-axis, so you can see. Now with sine, it's going to be along positive y if it's positive, like if you do plus and then sine. It's going to stretch along the positive y-axis, and if you change it into negative in the middle, it's going to be along the negative y-axis. It's straightforward, and you can see it's heart-shaped, okay? So this is all in here. And there's the examples that I just went over. Now there's lemma cones. I mean, there's a lot of stuff, okay? In trig, we go over this very thoroughly. This is not a trig class, but you need these in Calc 2. So there's lemma cones. Lemma cones are r equal a plus b sine theta. So if you know, in the case of cardioids, these were the same. Now they're different. R equals a minus b sine theta. R equals a plus b cosine theta. A minus b cosine theta. So if a is less than b, then the inner loop, it has inner loop and passes through the pole plus 3 sine theta. Look, a B. If A is less than B, the lemma cone has inner loop and it passes through the pole. Yeah. So 2 plus 3 sine theta. It has inner loop and it passes through the pole. If A is greater than B, then you have no inner loop and graph does not pass through the pole. No inner loop, so if it's R equal, just switch these two numbers around, 3 plus 2 sine theta. Three and 2. Alright, so no inner loop and it doesn't pass through the pole. That's vice. Of course, if you do cosine, it's going to go along the x-axis, just like cardioids. So if you do cosine, same thing, same features, okay? And if A and B are equal, then it's a cardioid, okay? Now roses, I explain roses thoroughly here, so I want you to go through that. R equal A sine n theta or A cosine n theta, where n is greater or equal to 2. Why? Because it's one. If it's a 1, it's a circle. If n is odd, the number of loops is n. If n is even, the number of is 2n. Okay. So for example, if say you have R equals 3 sine 3 theta versus R equal 3 sine 2 theta, for example. So this is n is odd and this is n is even. So let's see. So it's 3 sine 3 theta. So it has how many petals? How many loops? 3. N is odd. Now if as n is even, so this 2, we're going to have twice as much loops, 4. And there's a way to knowing this by hand, by doing the math. Okay, so these are, could be cosine, it doesn't have to be sine. This is page 27, the handout on this. To sketch a rows of form like sine 3 sine 3 or 3 cosine, whatever. If n is odd, you have n loops and petals. We just talked about. Find theta such that sine theta equals 1 or cosine n theta equals 1. For instance, in this case, sine 3 theta equals 1. So sine pi over 2 is 1, right? So 3 theta is pi over 2, so theta is pi over 6. This gives you the center line of the petal, of the first petal, so pi over 6. Petals are equally spaced, 360 degrees over n. If n is odd, it is odd in this case, so what's 360 divided by 3 is 120. So this is 30 degrees, then you need 120. So what's 30 plus 120? It's 150. So this would be the second one, that's 150. And then I add another 120. What's 150 plus 120? It's 270. So this is 270 right here. Right? 270. Okay, so there's 1 petal, 2, 3. Find R when sine n theta equals 1 or cosine n. So what is R? If this is 1, then R is 3. So then you mark 3 units on each petal. 3, 3, 3, and then you draw your loops. As simple as that. And you can graph it and see what I'm talking about. Okay, And there's lemniscates. You can check those out. And this is just switching from polar to from rectangle to polar. You can do that. And there's also symmetry. You can check symmetry. If a polar equation is unchanged when theta is replaced by negative theta, we have symmetry about polar axis and so on. Please read that. I take that because there's a lot of stuff and I cannot go over everything in polar, but that's enough, okay?